Yeah. So the books that we are going to be following this semester are Reinforced Concrete Design by Pillai and Menon, and Limit States Theory and Reinforced and Design of Reinforced Concrete by Shahan Karve. Uh, so I've been taught reinforced concrete by one of the authors of the book that you see on the left, that is Professor Devdas Menon. So whatever comes out of me in this course,
Bhargav, we can't see your screen.
okay, a moment. Now,
Yeah.
yeah. So these are the two books that we'll be following this semester, and like I have learned reinforced concrete from one of the authors of the book that you see on the left, Professor Devdas Menon, and whatever would come out of me in this course is more or less from the source from this source. So just like we had an IS code, just like we had an IS code, IS 800 for the design of steel structures. Similarly, we have a code IS 456-2000 named Plain and Reinforced Concrete Code of Practice. A number that's easy to remember, IS 456. So in last semester, we already discussed the various purposes of a code, which includes but not limited to laying guidelines for design and construction of structures, ensure adequate structural safety, and so on. So we've already discussed this. But one thing that is shown this semester is we are going to use the code more than we did it last semester. We are going to have to refer to this code numerous times. So I just suggest that you can keep in hard or a soft copy, whichever suits you. And time and again, in almost every chapter, we are going to go back to the code and see what it says, and then learn design accordingly. So similar to the theory and design of structures 5, in this course, we are going to primarily work on developing a background on the principles of structural engineering design. To start with, we are going to understand theories and concepts. And as we move on, this semester, we are going to try to have some hands on design experience through assignments. So the entire coursework that you had last semester was based on a series of quizzes or a series of tests. But this time, perhaps we'll try to incorporate assignments so that you actually get a feel of how to design various elements and very common elements that you used in almost all your design projects like beams, slabs, columns, footings, and so on. And then I'm sure you already must have had some background as to how to detail these elements, but nonetheless in this course we'll just get get uh, get get an actual feel of how these elements are detailed and designed so that you won't have anything else left in terms of understanding the drawings. And of course, time and again I will be sharing with you various real world open-ended issues that we face as engineers and as architects, and as we work together, the sort of issues that we face and how we tend to resolve them. So talking about the syllabus is split into four sections. The first one is concrete technology. Now I believe you already have learned this before. This is all about what is concrete, what are the constituents of concrete, then the details of each of the constituents, specifically about concrete, the grades of concrete, the purposes and types of additives in concrete, the use and purpose of special cement, so various types of cement, various types of concrete, then the process that is involved in concreting, right from transportation to placement to compaction and finally curing. So, I understand from my previous experience that you've already learned this before, but I'm not sure if there has been any change in the syllabus lately, and for some reason you haven't, learned these things before. So, would anyone please like to add to it? So, have you already learned it, or is this something new to you?
We learned the basics of concrete technology in second year.
Okay.
But like topics like transportation, placement, and like storage of it, like those are not.
Okay. So basically, you have learned about concrete, but perhaps you've not learned about concreting as to how concreting is done. Okay. So we'll brush through. See, anyway, we are going to brush through all everything, irrespective of you've learned it or not. But we'll focus on what you've not learned. So we'll focus on concreting. Uh, so the next subtopic, which carries the highest weightage in the examination, and in general, in terms of understanding reinforced concrete, is the design of primary structural elements. Okay, so we are going to learn the design of each of the elements from beam to slabs to columns to footings, and then we are going to have a very brief introduction of precast concrete elements and steel composite construction in buildings, its applications, its limitations, and so on. So the way I approach it is so it's a very fresh start, and I look at this as the first, uh, you know, I look at this as the point of inception because uh, so that we are not in a hurry right now and we get ample time to focus on what is more important and what needs more presence of mind and what needs more attention in terms of understanding. Uh, this is the numerical part of this course, and one of the guidelines that the university has given is the above elements are to be taught with minimum calculations and with emphasis on making correct structural drawings and good structural planning. So I'm gonna try to I'm going to try not to stick to my habit of getting into a lot of calculations or numericals, and we're gonna keep it to as minimum as possible, the minimum calculations that you require to design any element. uh, Next is I believe even this is something that you might have an introduction to, that is grid floors, rectangular grids, diagrids, and then different types of slabs, which again is not something very novel. uh, so we'll discuss different types of slabs like flat plate, flat slabs, and beam column slab, uh, and then again the applications and limitations of each of these. So as usual, we start with why. As to why do we see so much of reinforced concrete around us? Well, concrete undoubtedly is the most commonly used structural material. But how common it is, or how much part of our daily lives it plays, is perhaps not known, or rather not realized. Now, structural concrete is used extensively in the construction of various kinds of buildings. Example given: stadia, auditoria, pavements, bridges, piers, breakwaters, dams, waterways, pipes, water tanks, swimming pools, cooling towers, bunkers, silos, chimneys, communication towers, tunnels, and alike. So almost all the types of structures that we see around, can be built with concrete. Now just look at the place that all of you are sitting. So almost all of us are going to see concrete around us. In very special cases, a few might also see steel structures. So concrete is consumed at a rate of approximately 1 ton for every living human being. And we do not consume any other material except water in such tremendous quantities. So that is how common concrete is. And if there is a material which is so commonly used, so you as architects obviously should have an understanding of how is this being designed so that you can incorporate it in your architectural design. So let me ask you first, why is it called concrete? Like what comes to your mind when you hear the word concrete? You can also give an example. So what is so forget about engineering in general. What does concrete mean to you?
Something that's like stable and unchanging.
Yeah.
It gives an idea of like a strong and real thing instead of
Yes.
anything.
To give an example, I have got concrete answers. which means that I have a very solid answer. I have an answer that is stable on a geometry. So concrete means something that is solid. Now, in terms of defining it as a construction material, it is any solid mass which is made using a cementing medium. The picture that you see on the right is just a general depiction of what could be, uh, what nominally or what typically could be the percentages of various constituents of concrete. So the first thing that we have in the largest quantity is gravel, which are also called as coarse aggregates, which constitute about 35 to 45% of concrete. To fill in the spaces between these coarse aggregates, we have sand, which is also called as fine aggregates. And then we have some amount of water, and then cement, and then air, which is naturally entrapped while producing concrete or while placing concrete. So, water and cement work together as a cementing medium, and then it holds these coarse aggregates and fine aggregates together. So we have been using this material for about 150 years. So we have a lot of experience with this material, and with the advances in concrete technology, today we are able to produce various kinds of concrete that can be used for various purposes. Now, a natural question arises as to why is this guy so famous? Now, the first answer that comes to my mind is it is highly durable. So what I mean by durable is it has the ability to resist weathering action, chemical attack, abrasion, while maintaining its desired engineering properties. Okay. Now let us take the example of steel. Now one of the most common problems with steel is that it corrodes. It corrodes every now and then because it is not durable, and especially in harsh environments, for example, in waterfront structures, it poses a lot of problems. And on the other hand, and concrete on the other hand, is not only durable under normal conditions of temperature and pressure and environmental conditions, but also under hostile environments. The next thing is the ease with which it can be cast into various shapes and sizes. To cast any shape of concrete, what we practically need is a mold that can take that shape and a good method in which the concrete can be compacted. If these two are, if you can take care of these two, then I believe it can be cast into various shapes and sizes. And then, of course, the cost factor, which kind of spearheads the use of concrete, the extensive use of concrete. So the relative economy and the ease of availability. All the constituents of concrete that are required are available almost everywhere, and and that is one of the reasons why it is so extensively used. So this was in terms of general behavior of concrete, but in terms of its engineering behavior, its main strength lies in its compression bearing ability. So this particular compressive bearing ability surpasses that of traditional materials like brick and stone masonry. Now, as I said before, with the advances in concrete technology, it is now possible to produce wide range of concrete grades which vary in mass and density and also compressive strength. So the compressive strength that we could we could uh, say develop without too much of difficulties is in the range of 10 to 100 megapascals. Now, normally in very high-rise buildings, so in normal structures, one or two storied structures, the grade of concrete that is commonly used is M20, M25. Uh, in very high-rise structures, in most of the structures that we do, which are more than 60, 65 levels, we normally start with M70 or M60 grade of concrete. And then as we progress upwards, we sort of reduce the grade, say from M70 to M60 and then from M60 to M50. The thumb rule that we follow while doing this is for, say, one third of the structure, we have a higher grade of concrete, the lower one third. Then the middle one third, we have a lower grade of concrete, say M60. And then for the top one third, we have the lowest grade of concrete, say M50. So these reduction of the grades is normally done only for vertical elements. The reduction in the grade of concrete is done for walls, it is done for columns, and it is done for link beams. But for flow systems, that is for gravity, that is for slabs and flow beams, we normally stick with a single grade of concrete throughout the height of the structure, which normally is either M30 or M40. So, of course, it comes with its own set of limitations, and the worst one being concrete is remarkably weak in tension. So, its tensile strength is approximately one tenth of its compressive strength, meaning that if we have M40 grade of concrete, which means that the compressive strength of concrete is 40 megapascals. So, I hope you understand what M40 is. M40 is mix 40, and 40 is the compressive strength of concrete. So, if its compressive strength is 40 megapascals, its tensile strength is approximately 4 megapascals. So it is remarkably weak in tension. And now this limits the application of plain concrete as structural material in situations where significant strains and tensile strengths and stresses do not develop. So if we have to use only plain concrete, it practically can be used only in situations where there's compression. Wherever there's tension, concrete is bound to crack, and it cannot be used. But then we do have a solution for this, which is reinforcing the concrete. Just a minute. Yeah. So we've partially solved this problem by reinforcing various concrete elements so that it can now be used not only in compression but also in areas where we expect tension, either direct tension or say flexural tension, which is indirect tension. So with this, uh, so actually concrete would not have gained its present status as a principal building material, but for the invention of reinforced concrete, which is concrete with steel bars embedded in it. Now, RCC is thus a composite material that has the ability to resist significant tensile stresses as well, which was otherwise impossible. Now, with along with the amount of steel that is to be put, the location where you put the steel is equally important. Normally, steel bars are embedded in the tension zone of a member, meaning that if we are dealing with a simply supported beam, we know from our understanding of bending moment that the the bottom zone of the beam is going to experience tension and is going to experience tensile stresses, and that is where we provide concrete. And that is why, if you've had site visits before, in most of the beams you will see larger amount of reinforcement at the bottom if the beam is simply supported. If the beam is either continuous or fixed, you will from our understanding of bending moment diagram, it will have a significant moment also at the supports. So it will have a hogging moment here, and it will have a sagging moment at the center. In that case, what we do is we provide reinforcement at the supports on the left and right, and we also provide reinforcement along the length of the beam at the bottom. If we have a cantilever beam, then we expect from our understanding of bending moment and bending moment variation along the length of a cantilever beam, we'll have a significant moment at the top of the beam, and therefore we provide steel at the top of the beam. Now, a natural question arises as to, so concrete is one material, steel is one material. How is it that they are so good friends with each other? What is it that holds these materials together? Now, these are two different materials. Like when we are using them together as composite, so what is it that makes them behave as a single material? And the answer to this question is the so-called bond between concrete and steel, which sort of ensures unified behavior. So This perhaps is a separate topic. There's a topic named bond that we study in engineering, which is a complete separate topic, which sort of gives a description as to how steel and concrete behave together as a single unit, and how to detail steel in such a way that both of them never lose uh, this quality named bond in either of the in any of the loading conditions. Uh, Now, perhaps the question that I want to ask you is, we could have used any metal. Now, steel is a metal, so we could have used any other metal, for example, aluminium, copper, or gold or silver, perhaps any metal. So, why is it that we use steel? Why is it that we use, say, iron and it's alloy steel? Why is it that we do not use any other metal? It's okay. The answer can be generic. Like, the answer can be here. It is the cheapest metal available. It is the most plentifully available metal. It's okay. I just want you to think on it and say something.
It is the most tensile and elastic material.
Okay. Is Do we not know of any material that is more tensile and elastic?
Among the metals,
Okay.
Maybe the change due to temperature is similar in both the materials, like the expansion or the contraction.
Yeah. What's your name?
Mehek.
Sorry.
Mehek.
So I have a concrete answer from Mehek that these two are good friends because they get angry and they cool down together. In terms of, in scientific terms, the coefficient of thermal expansion, which is the amount of expansion that you expect a material to undergo after increasing its temperature by, say, 1 degree. This coefficient of thermal expansion of concrete and steel are very close to each other. So, when reinforced concrete is subject to high temperatures, both of them expand together, and then when they're subject to low temperatures, both of them contract together. So there is no relative movement between these materials, or there is no relative expansion or relative contraction. As a result of this, the bond, which is very important for this unified behavior, remains intact. And it is because of this property of steel that it is extensively used with concrete for reinforcing it. Okay. Now, concrete as a material is very brittle. It cannot undergo a lot of deformation. So, an important thing that steel does to concrete, it imparts ductility. Now, time and again, we have learned the importance of ductility, especially in regions which are uh, prone to earthquakes. So, this implies that if a properly reinforced beam were to fail, then such a failure will be preceded by large deflections caused by the yielding of steel, and thereby giving ample warning before the actual collapse. Okay, so this is how steel sort of uh, enhances the engineering properties of concrete. Now, a natural question arises: uh, wherever there is tension, that is fine. I can use steel in beams. I can use steel in slabs. But then, why do I use steel in columns? Because concrete already has a good compressive strength, and then in normal gravity design, uh, columns are predominantly going to subject to compression. So why is it that steel is used there also? Well, though steel is strong in tension, but then it is equally strong in compression, and therefore reinforcing steel can also supplement concrete in bearing compressive stress, as in columns provided with longitudinal bars. So now, in so we just have to be careful about one thing when we're using reinforcing steel in columns. So we have learned about this property of steel that it tends to buckle. Whenever it's slender, there's a lot of load, it tends to buckle. And now we are talking about bars, so which are very slender. The radius of gyration for these bars is going to be very less as compared to the sections that we have worked with in last semester. Therefore, we are going to need something that will make sure that these bars don't buckle when they are under loads. And to take care of this, we use elements which are called as ties or transverse steel reinforcement that we use to make sure that the longitudinal bars do not buckle. And there's another phenomenon called as confinement. So concrete, whenever it is confined, see, a simple meaning of confining something is to sort of applying pressure from all sides so that it increases the compressive strength of that material. So whenever concrete is confined, so these ties sort of confine concrete, as a result of which its behavior enhances. So ties play a multi role here. The first one of the roles that ties play here is that they make sure that the longitudinal reinforcement does not buckle, and then they also enhance the compressive strength of concrete. So the only thing that has changed uh, in this semester is the material. The basic principles of design consideration, design philosophy, everything remains same. The only thing that has changed is material. We've just replaced concrete with steel, but the principles of design still remain the same. So the aim of this course, or the aim of reinforced concrete design in general, is to design a structure in such a way that it fulfills its intended purpose during its intended design lifetime. And the first thing is that it should be adequately safe, meaning that it should be strong, it should be stable, and it should be safe in terms of its structural integrity. And the next thing is that it should be serviceable. Safety is fine, but then the structure uh, has to be serviceable. It should be used by its occupants without a lot of discomfort, or rather, it should be used by the occupants comfortably. In addition to this, the structure should be economically viable in terms of its cost of construction and maintenance. And unfortunately for us, the last thing that is that it should be aesthetically pleasing and sustainable. So you see, naturally, there's a lot of room for conflict between architect and designer and structural engineer, because the the priority list is completely opposite. The first thing that you guys start with is that it should be aesthetically pleasing and sustainable, and then you talk about economic viability, and then we talk about, oh, is it really possible, in terms of is it really possible in terms of engineering and construction to build this structure. So there is naturally a lot of space for conflict between architects and engineers. uh, in the words of Felix Candela, the architect has no weapons to fight against the scientific arguments of an engineer. A dialogue between them is impossible, who speak different languages. The result of the struggle is generally the same. Science prevails, and the final design has generally lost the eventual charm and fineness and fitness of the material dreamed by the architect. So, since the lines of thought are completely opposite, uh, what would really help you is sort of understanding prima facie if the design that you're perceiving or envisioning is structurally possible or not. If you sort of get an understanding of that beforehand, then naturally you would the point is number one on the list, and number three perhaps on your list is you'll naturally try to incorporate this point number three in point number one. So while making the structure aesthetically pleasing, you naturally think of its safety and naturally think of its practicability in terms of construction. So So this is something that we've already seen in the last semester, but since it's a new start, it's a new material, and this it's just a good opportunity to sort of brush up as to why we are going to learn reinforced concrete and what are in general, not for this course but in general, when you will design structures, what are the things that you should know and you should be aware of while you know before you actually start your design. So for the engineering design, the first thing is that the structure should be safe. So the structure should be safe in terms of its strength, meaning that the possibility of collapse should be acceptably low. Now, this should not be under normal and expected loads like live loads and superimposed dead loads and so on, but also under less frequent loads like earthquake or extreme winds and accidental loads like blast and impact. Now, these things become increasingly important as you move from conventional low-rise structures to high-rise structures, or you move from conventional low-rise structures to long-span structures like malls, auditoriums. Like I'm really happy and surprised that a lot of you have been working on very special structures uh, in your design assignments or design courses. So these are very special structures, and they do need a special attention in terms of not only in terms of architecture but also in terms of structural design. uh, so it is not every day that we encounter these in our structural practice. So this becomes increasingly important when you are designing special structures, and so the structure should always be safe against collapse due to overturning, sliding, buckling, and so on. Now, the structure as a whole should always be stable under all the conditions, meaning it should have adequate redundancy, meaning that if a part of the structure fails, say if you have a certain region of the structure where your beam slab has collapsed, but there has to be alternate paths for the load to flow, meaning that it should have adequate redundancy for the redistribution of loads. What happens because of this is if one of the element fails, if you have adequate redundancy, the force has different paths to flow, and then the structure does not collapse progressively, meaning that the failure is limited to a local failure. It is not turned into a global failure. And therefore, it should have adequate redundancy for redistribution of loads. The next thing is about serviceability, which is related to the usability of the structure. The structure should perform satisfactorily under all the service loads, meaning that there should be no excessive deflection, cracking, vibration, impermeability, which is day by day getting a very critical concern in buildings, and durability. See, uh, if even if I tell you that if you see a deflected slab and I tell you as a structural engineer that the slab is completely safe and there's absolutely no, it has been designed, I've designed it, I've put a lot of reinforcement and it's completely safe, you can stay under it. The moment you see a deflected slab, irrespective of what anyone says, you're not going to be using it. And therefore, only designing it for strength is not enough. It has to be designed for adequate serviceability. Uh, Vibration is an important factor wherever you have, whenever the functional requirements are, for example, whenever you have the use of machines in your structure, that is when vibrations play an important role. Or whenever you're building a structure very close to, say, railway lines. So, it has to be, the structure has to be resistant to vibration, and you sort of make sure that vibration does not affect the serviceability of the structure. Perhaps one thing that I've not added here and I should have is fire resistance. Very important. Just a moment. Yeah. So fire resistance, which is important and it is an increasing concern in especially in all the metropolitan cities. The third concern is economy. Irrespective of how safe or how serviceable your structure is, if it is not economical, no one is going to buy it and no one is going to pay you money to build it. Now, increasing the design margins of safety can enhance the safety and serviceability, but increases the cost of the structure. So there always has to be a balance between safety and serviceability and economy. So, and that is why the diagram at the start. So there's always has to be a balance between the three, and that gives a perfect design. Again, this is so. See, optimization is a trial and error procedure. So design is a process of optimization, and in any design, certain criteria must be established to evaluate if the structure is safe, economical, or not. So the design considerations that we use in structural design are: the first thing is it has to have minimum cost, it has to have minimum weight, should be constructed in minimum time, using minimum labor, and maximum operational efficiency. Now, would anyone like to comment further as to why should a structure have minimum weight?
So that it doesn't buckle under its own load.
But we will design it for that, right? Like we know the weight, and therefore we'll make sure that it does not buckle under its own weight.
Same reason. Minimum cost. More the weight, more the cost.
Yes. So a very obvious answer is that larger weight implies that you've used larger quantity of material, which means that it is going to cost more. Any further answers as to why should it have minimum weight?
Less material waste.
Yes, yes, yes. We have answered that. Okay. So lighter the structure, lighter is the foundation that is required for that structure. And foundation accounts for about 3 to 5% of the total cost of the structure. So lighter the structure, lighter the foundation, and higher is the cost saving, and therefore minimum weight of the structure. So the basic design concepts that we are going to touch upon are, okay, again, we have seen this before. This is a quick revision. So the basic design concepts that, by the way, any questions until now? Are you guys awake?
Yes.
Yeah.
You're awake, right?
Yeah.
So, the one thing that I realized this last semester is I've lost complete connect with all of you in terms of, um, really communicating what I want to and really understanding if it has reached you. So that is something that is really challenging, and I'm still wondering as to how this gap can be bridged. Now, perhaps, do you okay? So how about other subjects? So, is there still a deficiency in terms of what is being taught and what is being understood, or it is just the way the subject is taught that because of which there is a deficiency between what is taught and what is. If I would check your papers, perhaps I would get a better feel of it. But nonetheless, now even in general, I get a feel that from your participation in the lectures that there is certain deficiency. Okay. Nonetheless, this is the task at hand now, and this is the way we have to learn. So, the design, the first thing that we're going to look at is the design philosophies. Uh, we have heard of these terms before: working stress method, ultimate load method, limit states method. Now, we are not going to get into what these are and what these mean, what is actually this philosophy, and when it is used, how it is used, and so on. So, just to give you a simple example, so working stress method, which is the oldest sort of uh, oldest, what I would say, a documented method of designing structures, is like buying a new bike and then you know riding it by walking alongside it. So not actually sitting on the bike and riding it. Just you hold it on your side and then you walk with the bike. Ultimate load method is like purchasing a new bike and then riding it for its entire lifetime without servicing it. And limit state method is like purchasing a new bike, riding it, and then maintaining it now and then. So
Bharat, I lost you. Can you just repeat
okay,
the example?
yeah, okay. So this is a very general example of the differences between working stress, ultimate load, and limit state method. So working stress method is like purchasing a new bike and then instead of sitting on it and riding, you just ride it by walking alongside it. Do you understand what I mean? So when your bike is punctured, the way you ride it, the working stress method is riding the bike that way. Ultimate load method is like purchasing a new bike and riding it for its entire lifetime without servicing it. Okay. And limit states method is purchasing a new bike, riding it, but making sure that you maintain it every now and then. Okay. So in limit states method, we take care of not only strength but also serviceability. Okay. So when I say that you ride the bike and you maintain it very every now and then, meaning that we take care of its strength and its serviceability. Okay. So what we are going to look at and what the method, the philosophy that has been followed for quite some time and accepted throughout the world is limit states method. Now, of course, there are even some advanced philosophies like performance-based design, which are used in very special cases using special studies and research papers, but they're not commonly adopted for all the structures because we have found that limit state method is sufficient for Gargar ke design. For nominal structures, which account for more than 90% of the structures, limit states method is sufficient, and this has been accepted all over the world. And we have an option in this course. We have an option of either studying the working stress method or the limit states method. And I was surprised when I checked papers, what about a couple of years back. So last year, I think we did not have an exam for theory of structure 6 because Corona had just hit, and we're completely clueless then. And I think there was no exam, there was no external examination for theory of structure 6. But a year before that, so we get random examination papers since it's a university exam. So I got about 120 papers, and more than 90% of them had used working stress method uh, to solve the paper, meaning that the curriculum wasn't working stress method. And no, it's not harmful in any way. We learn working stress method first, and then we jump to limit states method. But I was just wondering if in terms of picking it up in terms of what is used in the industry. I think going with limit states method is the best option for this course. So we are going to learn everything in limit states method. So the first thing is, what is a limit state? And since we are talking about strength and serviceability, obviously we are going to have limit states of strength and limit states of serviceability. A definition that you must have ratified by now because I've asked it a number of times. So limit state is a state of impending failure, meaning that the failure is about to happen, it has not happened yet. If that happens, the structure will cease to perform its intended function satisfactorily, either in terms of safety or serviceability. That is, it either collapses or becomes unserviceable. So what we have done is we have a set of states. If the structure achieves any of it, we will say that now the structure has reached either its ultimate limit state or serviceable limit state. I'm not sure if I gave this example before, but consider your phone, consider your mobile phone. It also has certain states of strength and serviceability. Okay, so if your phone falls, it breaks the display, it has reached a certain limit state of strength, meaning that now it is no more, it cannot be used anymore, and perhaps you have to either get a new device or perform a very rigorous repairs on it. So it is a limit state of strength. A, lim- a limit state of serviceability might be, because of some reason your touch is not responding properly. So you don't have to replace the phone altogether. You might just have some nominal repairs and then your phone is good to use. So similarly, for a structure, we define certain limit states of strength and certain limit states of serviceability. If we reach any of the limit states of strength, the structure cannot be used anymore and it either has to be demolished and built again or it has to undergo very rigorous structural changes. When we talk about limit states of serviceability, it means that whenever any of these limit states is reached, now it's time to service the structure and you can use the structure only after it is serviced. Okay, so let us look at what are these limit states of strength and serviceability. We had a similar list in steel, uh, like we have in concrete here. So the limit states of strength are flexure or bending. This particular state is significant when we are designing beams and slabs. Next limit state of strength is shear, which is important when we are designing beams. We also consider it uh, uh, in the design of footings. Another limit state of strength is torsion, which is again significant in beams. Next one is bond, which has to be adequate in all the members. And the last one is compression, which nominally governs in columns. So through various design elements like beams, slabs, columns, and footings, we are going to look at each of these limit states of strength. Talking about the limit states of serviceability, we have deflections. So we are going to make sure that any flexural element that we design is going to be adequate in terms of deflection, meaning that it will not deflect above a certain limit that's prescribed by the code. Another one is cracking. Cracking is of significant importance in the design of footings because if for some reason the footing cracks, the soil is rich in minerals, sometimes in water, and there's a high possibility of the water getting in touch with our reinforcing steel and thereby corroding it, degrading the structural strength of the footing, and hence cracking is very important when you're considering footings. Vibrations, fire resistance is important in almost all the structures, and finally durability. Uh, so I think we'll just take a small break here, say 5 minutes break. This is something that we had learned last semester, but obviously there was perhaps that was the first time that we looked at all these concepts. And I think this is a good opportunity to sort of brush through all these and before we start into the design of concrete. So we'll just take a small break, 5 minutes, and then we'll resume by say 10:05.
Bhargav, can you go back to the limit state slide?
Yeah.
Yeah, that's it. Yeah, that's it.
Okay, shall we resume? Are you guys back?
Yes.
By the way, isn't this the semester before which you go for a project somewhere and then you have that exhibition?
Yeah,
So are you missing? So is it cancelled for this semester? Is it that it is postponed or it is cancelled?
it's cancelled.
Okay, I think that's a little unfortunate because uh, I really saw great exhibitions in the last 2 years, and even I just the students have really good experiences, and the place are amazing. I think last semester they went somewhere in the northeast.
Yeah, they went to Nagaland.
Yeah, and the exhibition was amazing. And I was talking to Meenal the other day, and she told me that the output from students in terms of their studios is greatly improved, and I was happy to know. So yeah, so in terms of design, what is a theoretical perfection is that the capacity is equal to demand, meaning that the structure is perfectly capable of what is going to be subjected to it. But for safety and to take care of a lot of uncertainties pertaining to the material, members, the structure as a whole, and the loads that are going to be applied, the capacity has to be slightly greater than demand. But the question is how much? Because, like we have said sometime before, we can always design a very safe structure, but it will always come at a cost, which perhaps could be avoided. And then the question is always how much should the capacity should be greater than demand, or should the how much should be the safety of the structure. Now, naturally, the capacity comes from the material and the geometry, and the demand comes from loads and deformations. So we uh, come to this term called as characteristic strength. So when we say that concrete is M40, so 40 is undoubtedly the compressive strength, but 40 is the characteristic compressive strength. Okay, we have looked at this example before, but another try to understand it better. Say I want to design a concrete that has a characteristic strength of M40. What it means is that if I do the concrete technology and design it, and I do you guys know how concrete is tested? Like how is the compressive strength of concrete tested?
Cube test.
Yes. So in India, what is commonly done is the compressive strength of concrete cubes. So if I what it means to have 40 megapascals of characteristic strength is that if I cast 100 cubes and if I test them one by one, only 5 of these cubes will have a compressive strength of less than 40 megapascals. Okay. Now one thing is obvious. Though it is though the ingredients are same, though the cubes are of the same dimensions, though the machine is the same, the type of loading is the same, still you can expect each of these cubes to have a unique value for compressive strength. Do you get what I'm trying to say?
Yeah.
Yeah.
So, and the reason is that concrete is a heterogeneous material. It is not like steel. So, if you had to test two different samples of steel, perhaps you would get a very similar stress strain curve. But when you test concrete from the same ingredients, from the same uh, with using the same machine, using everything remains the same, and still we get different values of compressive strength. So when I test say 100 cubes, only 5 of them will have compressive strength lesser than 40 megapascals. That is what means to have a characteristic strength of 40. Okay. Now, you must have seen this curve a lot of times before. Can you remember one instance when you've seen this curve? Do you remember your
Yes.
Do you remember your quizzes?
Yes.
So perhaps this is not your curve, but then I just pull out any of the curve quizzes. Just a moment. Can you see my screen?
Yes, yes,
Can you see the Chrome screen?
yes.
Yeah. So normally when you have a sample space and you do something with that, say example conduct a test. Now your test was to answer these questions. The test of concrete was to give its compressive strength. So normally you get a curve like this, which is called as normal distribution curve, wherein maximum number of your sample space elements exhibit the median value. Okay. A very low percentage of your sample spaces exhibit a very high value and also a very low value. So you get this curve, which is called as a normal curve. Okay. Now, depending on this curve, I could set a passing percentage. Okay. So I would say that this is 5. Okay. So 5 is the passing percentage. So everybody who have scored more than 5 is pass, and everybody who scored less than 5 is fail. Similarly, when I say M40, meaning that out of those 100, 95 of them have passed with a strength of more than 40 megapascals, and 5% have a strength of less than 40 megapascals. So that is what means to have a compressive strength of 40 megapascals. Just a moment, okay? Yeah. So do you understand this better?
Yeah.
So basically, it's just the passing percentage. Okay, 40 megapascal, 40 is the passing percentage. Now, why is it that we select a lower value and not by a higher value? Okay. Now, I've said this time and again. Every time we underestimate strength and overestimate the demand. Okay, meaning that we are always going to underestimate the strength of the material, the strength of the member, and we are always going to overestimate loads. Okay, so we are looking for a value that, in worst case, also will make sure that it is satisfying the sort of strength that we expect out of it, and hence we take a lower bound strength. Okay, we could have taken 95 as a passing percentage, but that would be a disaster because in that case you are expecting the material to behave in uh, in a very particular way. For example, if for your class I said the passing percentage is 95, it's going to be a disaster, right? So we are looking we are looking for a lower bound material strength, a strength that you can expect the material to adhere to. Okay. The opposite of this is loads. Similarly, uh, it is very similar to the concept that we saw before, but here we are looking for a upper bound of load, meaning that 95% of the times the load that you can expect in a particular structure is lesser than this value. That particular load is called as characteristic load. Okay, so the value of load which has 95% or 95% probability of not being exceeded during the life of the structure is called as characteristic load. Now, our resistance or our capacity should always be greater than load. Okay, but if it is much greater, we'll have a lot of safety, but we'll have a lot of uneconomy. Okay, so we have to reach a certain we say compromise between the load and resistance such that we have safety as well as economy. Okay, and that economy is what you see in the lower graph, wherein there is a slight overlap between the load and resistance, meaning that there is a slight possibility of failure, meaning that the possibility of failure is acceptably low. Okay, we can always design a structure that is completely safe. Like never, we can design a structure for 100 percentile load, but it is going to be highly uneconomical. Okay, and that is the reason we design structures for 90 percentile load and 5 percentile strength, and that is what gives us economy. And this is achieved through the use of a series of partial safety factors. Okay, to understand the concept of safety factor, taking a look at the stress strain graph of steel, of mild steel that we've done numerous times before. We know that green. Does someone remember what this green point is? What is the stress corresponding to this green point?
Yield stress?
Yield stress. Yes. We know that this is the ultimate strength. This is the ultimate capacity. Okay. We don't want to go beyond that. We define this as the ultimate stress, meaning that if the stress in steel has reached this value, we'll stop the use of the structure. We'll not load it further. Okay. We know that this is the ultimate capacity. But I want to have some safety margin. So what I'll do is I'll divide it by a partial safety factor for material. So I'll move from green to blue. So that even though, okay, if there's 415 is the grade of steel, if I know that 415 is the yield stress, but still I don't want to touch 415, I want to say touch 415 divided by the partial safety factor for material. That will give me some sort of safety factor. Okay. Now talking about loads. If for a certain loading, I know that the stress that is going to develop in the material is at the position of the pink. What I'll do is I'll use a partial safety factor to sort of enhance this load. So I'll multiply it by a partial safety factor for loads to move from a working load, which I know is going to act on the structure actually, to a design load. Okay. And then why do we do it? Like, why do I need the partial safety factor for material and why do I need a partial safety factor for load? I need a partial safety factor for material because there, especially for concrete, there is going to be a deviation of material strength from the assumed value. If you say M40, there's no guarantee that it is going to give you 40. It might give you 45, 50, 35. So, there's always this possible deviation. And the more heterogeneous the material, the more is the possibility of deviation. And therefore, to account for this, we use this partial safety factor. There might be manufacturing tolerances, imperfections in the material, and so on. We need partial safety factor for loads because we have assumed a certain value of load, but it might be different. See, I might have designed my structure, say, for the use of a hostel, but tomorrow it is converted into a classroom and the live load has completely changed. and therefore there's always a possibility of there's always a possibility of deviation of loads from the specified values. Then there can be a variability in load combinations. Now I in my design I have assumed 1.5 dead load plus 1.5 live load. Okay, but it might happen that the live load has shot up much higher. Say when I convert from a hostel building to a classroom, my live load has shot up by say 2 times, 2.3 times, and so on. So there's always a possibility of variability in load combinations. So to account for all these factors, we underestimate the strength and overestimate the load. Okay, looking at these, so this is precisely what I've this is just a summary of what we've discussed. The strength should always be greater than the capacity or the load effects, meaning that the design strength should always be greater than the design load effects, and we always underestimate the strength, overestimate the loads, and therefore the strength we design by partial safety factor, and demand we multiplied by partial safety factor. So characteristic load, when it is multiplied by partial safety factor, we get a design load. The characteristic strength when divided by a partial safety factor gives us design strength. Simple. And your design strength, that is your green block, should always have a value that is higher than the red block. So what are these partial safety factors for material? Now, in last semester, we looked at gamma M0, gamma M1, and so on. So these partial safety factors were based, so the material was same. So the element was steel, the bolts were steel, okay, the welding material was also metal. So everything was same. Therefore, we did not have different partial safety factors because there was a single material. The partial safety factors were based on how it fails. Okay, if it fails in a ductile manner, we had a partial safety factor for 1.1. If it is a brittle failure or a sudden failure, we had a partial safety factor for 1.25. Okay, now here we have two different materials, and obviously these different materials need to have different partial safety factors. Concrete has a partial safety factor of 1.5 and steel has a partial safety factor of 1.15. Okay. Now, after explaining all of this, can someone please answer me as to why concrete has a higher partial safety factor? Why this 9 Safi with concrete?
A higher partial safety factor means that we'll account for a larger variation in load because we don't exactly know what the exact properties of concrete are going to be. That's why.
Yes, yes, that's a very concrete answer. A larger partial safety factor implies that concrete is less reliable, and therefore we have to have more partial safety factor here. Therefore, we are penalizing ourselves. The reason is that concrete is heterogeneous. Okay, steel is a single material. Concrete, so you are putting coarse aggregate from one source, fine aggregate from other source, water from some source, cement from one source, mixing them together, and then you cannot expect concrete to behave exactly the way you want it to behave. It is going to deviate. To take care of that deviation, we use a higher partial safety factor of 1.5. Okay. Now, this is something we've seen before. Partial safety factor for loads. If it is dead load, it is 1.5. Live load 1.5. When different loads are acting together, we reduce the partial safety factor because the possibility of all of these loads acting in a higher proportion together is less. Therefore, when we consider dead plus live plus wind earthquake, we use 1.2, meaning that we'll have 1.2 dead plus 1.2 live plus 1.2 earthquake. When you're using only dead plus wind earthquake, then you will have 1.5 dead plus 1.5 earthquake. Okay. Last time I explained you, when we are considering overturning, that time dead load sort of does not, dead load works in our favor. Okay. That is the case when we use zero point 0.9 safety factor. We don't have to get into the details of it. This is a design consideration, and perhaps it's not a very useful information for you. So I'm not going to emphasize on that. What you want to remember is, okay, dead plus earthquake, 1.5 dead plus 1.5 window earthquake. For this is for all the ultimate limit states. When you're talking about limit state of serviceability, We are interested in what are the actual deflections. When a structure is when a structure is collapsing, we are not interested in deflections because anyway the structure is not going to be used now. So we are interested in deflections when it is an actual use, and therefore for all limit states of serviceability, we have one. We're not going to get into point eight and why it is used. Just remember that for all the limit states of serviceability, when you are calculating cracking, when you're calculating deflection, partial safety factor is for loads is one. We consider the actual load, not a higher estimate of the load. Now, we began the last semester with stress strain curve of steel. Similarly, we have a stress strain curve for concrete. Okay, simple parabola rectangle. Well, it is a very simplified way of presenting this curve. Like we have done a lot of actual tests, and the curve never looks so ideal. It's always it's parabolic. Yes, it's parabolic, but every time we get a different sort of nature of the parabola. This is a simplified curve that is given by IS code. Okay, now you see three curves here. Let us focus on the topmost. Okay, the topmost curve is what is called as a characteristic curve of a cube. Again, sticking to the example of M40 concrete, meaning that if I test an M40 concrete, I can expect the curve to behave this way. Okay, so it is parabola up to a certain strain that is 0.002, and then it does not, just like steel has this yield stress where it does not uh, resist any further increase in the deformation. Similarly, for this there's an increase in the strain without any increase in the stress. Okay, so we have a parabola rectangle curve. Now the US code, for example, consider this as a straight line and a rectangle. So it does not consider this as the parabola. It just considers this as a straight line, as a linear and then rectangular curve. So it depends on the code. So we simplify it because practically it is not possible to generate a unique curve for every concrete that you produce. Therefore, there has to be some simplification. So this is a simplification. So this is parabola rectangle curve. It is parabolic up to a strain value of 0.002 and then it is linear. Okay. Now, the question is, suppose you test a concrete block, you get a certain curve, that's fine. Do you expect concrete to behave in the same way when it is used in a member that is quite large as compared to the concrete block and that is subjected to very different type of stress? When you test a concrete block, it's very simple. You just place the concrete block in the machine, you apply compression, it breaks, you record what is the compressive strength. But in an actual building, you are going to use the concrete for, say, a beam. In that beam, it is not going to have only compression. It is going to have compression, tension, shear, and so on. So while testing, there's only one type of stress, which is compressive stress. The size of the cube is so small. Actually, the size of the member is so large. Plus, it is heterogeneous. Had it been steel, we would understand. Okay, it is going to behave the same. But it is concrete, it is heterogeneous. The size of the uh, member matters. Now, just to give you a simple example, Indians use we use concrete cubes, and in United States they use concrete cylinders. Okay. Now the difference is that our cubes are, let me put it the other way. The cylinders, if made from the same concrete, like today in the lab, if I cast a cylinder and if I cast a cube, the cylinder will have a strength about zero point 0.8 times out of the cube. So just by changing the shape, I'm getting a different stress value. Okay, it's that heterogeneous. So now we have to have a certain factor to account for this size effect, for this loading effect, and uh, unlike steel, the behavior of concrete sort of changes over time. Thus, it's this the strength sort of increases first, then it attains a peak value, and then because of temperature and shrinkage, the strength sort of goes down. Not getting into that. The point is that there's going to be a lot of difference between the behavior of the cube and between the behavior of concrete in the actual structure, and therefore we have to have a certain factor. So then we say that, okay, I will say that I will use only 2/3 of the strength that the cube gives me. Okay, and therefore we move on from characteristic curve for the cube to characteristic curve for the structure. Okay, so we are using only 67% of what I get in a testing lab. To this 67% or to this 0.67 FCK, I further divided it by the partial safety factor, which is 1.5. And 0.67 divided by 1.5 is 0.447, which is approximately 0.45 FCK. This is my design stress. Okay, meaning that if I cast the cube, test it in the lab, and I get a stress of say 50 megapascal.
जो मैं लेक्चर ज्वाइन देऊ जे तू खाली जो नाही
Okay, so if I test a cube in the lab and I get a strength of say 50 megapascals, the actual number that I'm going to use in my structure is 0.45 times of 50, which is 22.5 megapascals. Okay, so there is such a safety margin when we are designing structures. So this is just about material, but there's also a lot of variability in the quality of construction, in the way it is designed, and so on. Now, like one of our professors used to say that almost all the buildings that we design today are standing only because there's a very high safety factor. Because there is a lot of bad design, there is a lot of bad construction, there is a lot of bad way of bad maintenance. And had there been no safety factors, we would not see so many of our structures standing today. It's only because of these partial safety factors that our structures stand. Okay, so this
Bhargav,
yeah,
I did not understand what did you say that 0.45 into
go on.
50, like that becomes the partial safety factor.
Sorry.
The point when you said that 0.45 into 50,
Yeah,
or something, I did not understand that.
yeah. So if I cast concrete, put it in a cube, let it cure it, and then I test it in the lab. If I get the compressive strength as 50 megapascals, meaning that the cube crushed at a stress value of 50 megapascals. For the same, if I'm going to use the same concrete in my structure, the strength that I'm going to assume is 0.45 times of 50, which is 22.5. Meaning that if my cube uh, crushes in compression or my cube fails at 50 megapascals in the lab, I will assume that the same concrete will fail at 22.5 megapascals in an actual structure. And I will size my elements accordingly.
Is that to account for the tension in the actual members while constructing?
That is to take care of hundreds of factors. The most important being concrete is a heterogeneous material. If you test a cube and then you test a column, so if you say you actually cast a column and then you have a huge dinosaur machine that can test your column, okay, you will get a different value of stress. You will get a different value of strength. So this effect is called a size effect. Steel does not behave that way. You test any size of steel, it is going to give you the same curve, almost the same curve and almost the same stress. But concrete has size effect. So the strength of concrete differs with the size of the element that you're using. Okay, first is that. Second is that in a compressive strength test, you are subjecting it to only compression. Okay, but in actual structure, the stress is not going to be uniaxial. It is going to be a multi-axial state of stress. It is going to be subjected to compression, the compression in one direction, tension or compression in the other direction, shear, and so on. So there's a multi-axial. The state of stress is complicated in the structure. It is not a simple cube subjected to compression. That is second thing.
So that is the reason becomes the half of the strength, half of
Yes, yes, that is the reason why we are moving from FCK to 0.45 FCK. Okay. The third thing is, in while testing a concrete cube, the loading is short term, meaning that the test is over in a couple of minutes. In an actual structure, the loading is very long term, and you don't load the structure immediately. First, you construct the structure, and then dhire dhire you put all the superimposed dead load. Then dhire dhire you start putting live load. The property of concrete is that its strength sort of varies with time. Okay, as the concrete cures, like there's an immediate gain of strength between day 0 and day 7, and then substantial and then a considerable increase in strength from day 7 to day 28, and even after that the strength increases further until it reaches a peak, and then the strength reduces. So
Oh,
the
Bhargav, so
yeah,
the entire point of doing the two-third is to take into consideration all of these uncertain
yes, yes,
factors.
yes, yes, and then
So
further,
if we knew all these properties of concrete, like if, like for example, steel, we know all of those properties,
yeah,
then we won't do this two-third thingy, right?
yes, we won't, and we don't do it. Like in the next curve, you'll see that this is the design stretching curve for steel. We don't do this two-third. We just divide it by partial safety factor. We get 0.87. That's it. Because there is a lot of uh, uh, what I would say, there's concrete is heterogeneous. There's a lot of uncertainty involved while using a heterogeneous material, and that is the reason why we have a very high partial safety factor for concrete.
Okay, yeah.
Okay, and
Also, I didn't understand the thing you were saying between difference between testing a cube and a cylinder.
yeah, we'll get to that. So, just to complete the list of some important reasons why we do it. What was I going to say? Yes, steel is an industrial product. It is produced under controlled conditions. For more than 90% of the structures, concrete is cast in place. Concrete is manufactured in the site and then it is used. So there's no quality control over the, or I wouldn't say no, but there is very less control over the quality of concrete that is being produced, especially on site. Okay, the the sort of batching that is done, or there's a volume batching, way batching, and so on. So it's very approximate. The quantities of cement, water, coarse aggregate, fine aggregate that they mix is very approximate. They have a general understanding that okay, with if I mix this, I'll get M20. In majority of projects, there is no testing. It is simply based on some it is simply based on calculations, hand calculations, and in general the understanding of the contractor with his experience. Okay, so if I say okay M25 use करना है, the contractor might have used M20 before. He just say हाँ थोड़ा सीमेंट ज़्यादा डाल दो. Okay, so that is what happens in majority of the buildings. Again, so there's a lot of variability. So who is going to account for all this? That's a partial safety factor. And then so to answer your question, uh, when okay, let me give this example again. So if I'm casting a standard cube, which is 15 centimeter by 15 centimeter by 15 centimeter, and then I cast a cylinder, uh, which as far as I can remember, is approximately is 15 centimeters in diameter and 30 centimeters in height. That is a standard cylinder. Okay, so to give what a cylinder looks like. So this is a concrete cylinder. And okay, perfect. So the size of a standard concrete block is 15 centimeters by 15 centimeters by 15 centimeters, and that of a cube is 15 centimeters in diameter, and the height is 330 centimeters. Okay, so when we mold this, or when we get it mold from the same, uh, like from the same mixture, okay, from the same concrete, if we cast a cylinder and a cube, if you get say 40 megapascals from the cube, what you can expect to get from the cylinder is zero point 0.8 times 40, which is 32 megapascals.
Can you repeat?
Okay. So what I've done is I have taken coarse aggregate, fine aggregate, mixed them, put water, put cement, made concrete. Okay. Now I've put some concrete in the mold of the cube. I've put some concrete in the mold of the cylinder. Basically, I'm casting a cube and a cylinder out of the same concrete. I take the concrete block and test it. The machine starts, it starts loading, the concrete fails at 40 megapascals. Okay. I can expect the cylinder to fail at zero point 0.8 times 40, which is 32 megapascals. Meaning that if I now remove the concrete cylinder, concrete cube, if I place the concrete cylinder, start loading, I'll expect it to fail at a value close to 32 megapascals, which is zero point 0.8 times what I got in the cube. So the point being, the strength that we get is a function of size. Okay, the like a cylinder is different from a cube. The dimensions are a little different. So that is called a size effect. Now tomorrow, if you cast an actual 3 meter high column, which is 500 by 500, and you have a machine that can test it, you will get a different value for the same concrete that I just mixed. You get a different value. So that is called a size effect. Okay, so the way concrete will behave depends on its size. It is not like steel. The steel behaves the same way in every size. Concrete, it's not like that, and therefore we reduce it by 33%. So okay, if cube gives this in the structure, I will say 0.67 times whatever, and then partial safety factor for all the reasons that we discussed, we reduce it by 1.5 further. Is it clear now?
We take 0.45 of the cube then, right?
Yes, we take final product is 0.45 of cube. Is it clear?
Yes, but if the strength depends on the size, then why do we take the cube as a standard? So wouldn't the size differ with the application where the concrete is used? So shouldn't we test the concrete for that shape and size for which it is being used?
In that, what will happen in that is that there will be no standardization. So the size of the column, that the size of the column, beam, slab, whatever, can be like practically you can use any number. There's no limit to it. So we cannot have like different sizes depending upon the size of the member, because the first thing is there'll be no standardization, and second thing is we'll have a lot of things to deal with then. For example, now I am working on the sizes of columns, so I have to find some size of the column for a particular structure. For say for different sizes of columns, I have to consider some different number. So if I say I want to use a 500 by 500 column, my partial safety factor is 1.5. If it is a 600 by 600 column, my partial safety factor is 1.7. So that complicates everything. So what is done instead is a very simple approach. Okay, irrespective of what you're using the concrete for, take this cube, test it. Whatever you get, use 45% of that. So that approach is simple but conservative. Okay. And like I said before, in majority of the structures, there is no testing. Forget about this concrete block. And therefore, we have to be conservative because we have to see the ultimate objective of the code is that it should be used. And if it is simple to understand, only then it is going to be used. If we introduce a number of factors, if we complicate the design, designers are going to be, they are going to be discouraged from using it. Therefore, to have a very simple, straightforward approach with minimum factors and maximum applicability, we only have one standard cube that we test. With the help of this cube, there have been hajar experiment, there have been hajars of papers after which this number has been decided, all after a lot of research.
Okay.
Ideally, what you say is correct. And on the same lines, like if it's a very special structure, on the same lines, what is called as performance-based design is done, which is again a design philosophy. Like we have working stress, ultimate strength, limit state. There's another one called as performance-based design, in which it's based on it's based on the performance of the material, in that particular member. So that's a very that's a very involved way of designing structures. For Ghar ki structures, you don't need it. Okay. Uh, Someone else had a question.
Yeah, so when you said that the cube or the column fails at the 40 megapascal, so under the failure of like point 0.8, that at 32 megapascal, so does that mean that it is out of those 5% of the characteristic strength that fails when the strength is M40?
Okay. So characteristic strength is a different concept. When we are when we are testing cylinder and cube, we are just looking at individual elements. Okay. If you're talking about characteristic strength, the characteristic strength for the cube is a different thing. The characteristic strength for the cylinder is a different thing. When we compare these two, we are basically just comparing single elements of different shapes. So it has got nothing to do with characteristic strength when we are comparing these two.
So when you said when the pressure applied is 40 megapascal, then how does it fail at 32?
So the cylinder fails at 32,
32, okay.
not the concrete cube.
And that is because of the size.
That is because of size. Of course, there are other effects also, which I don't want to get into. There's Platten effect, and there's the cylinder is slender as compared to the cube. A lot of other effects, but every the see uh, the fundamental is that the size is different. Okay, and therefore the failure value is different.
Okay.
In short,
So the 33% reduction that we consider, that is irrespective of the shape of the block, right?
yeah, that is it. So there's only one shape that is standard. There's only one standard shape that is used across all the testing facilities in India. That is a cube of 15 by 15 by 15. And irrespective of where the concrete is going to be used, to this actually this 30. Okay. Let's not go into more
Uh,
detail. Just
Now,
assume.
why I'm asking is we are just talking about a cube and the cylinder. So the 33% reduction, that is not because of the cylinder, right? It's a safety factor irrespective of the shape of the block, right?
Okay, so everything that we are doing in this graph is only for a cube. Okay, if we are working with a cylinder, we will use some different factors. See, you have to understand that we are moving from a standard specimen to an actual structure. So it has to be function of the standard specimen that you are using. The factors that you see on screen are only for a cube.
Okay.
If you select cylinder as your standard specimen, you will have slightly different factors. Okay, but since like we as a country use cube, and there's always good to have a comparison as to uh, what other countries doing, wherein they have had good results, they have good structures, and that is the reason why we just compare it to the cylinder. Okay, if we have 40, US has 32. US considers 32, we consider 40. Okay, so that's a different comparison. This is especially pertaining to a cube. When we convert from a cube to an actual structure, we use the factor of 0.67. So had we
Okay.
used a cylinder, so I see. Uh, I'm trying not to get into it, but just okay. I don't want to increase your confusion, but since you asked, when we are converting from a cube to a structure, we would use a factor of 0.67. When we are converting from a cylinder to a structure, we would use 0.85. Okay, so the factors are different. It depends on what is your standard specimen. Ours is cube. Use what is the factor that is given, which is 0.67. Reduce this 0.67 by partial safety factor, that is 1.5, you'll get 0.447, which is approximately 0.45. So if cubes gives, if I test it in the lab, I get 40 megapascals. In the actual structure, I'm going to use 0.45 times of 40, which is 22.5 megapascals. This is the baseline.
Got it. Yeah.
Okay, I think we have really overshot the time, but nonetheless, if you've understood what is being taught, I think it's worth it. There's only one more slide. Perhaps I would like to discuss this slide again in the next lecture. So I think it's best to stop right now. Just give me a moment. I'll take attendance. Okay, so that's it from my side for today. In case you have any questions, I'm here for a while. And in case you want to suggest anything regarding the way this course can be improved,